Ryan, blink twice if you're okay.
I can't hear you though.
They said somebody said that you look like you're in a hostage video. And
what?
Gail Carlos says blink twice if you are being held hostage. Oh, he blinked twice.
No, I'm not being.
Astronauts to the moon.
Ignition sequence start. 3, 2, 1.
Houston, we have a problem.
Liftoff. We have a liftoff.
We copy you on the ground. You got a bunch of guys about to turn blue.
What you're seeing here is a mirage.
What's going on, everyone? It's Jaron from jeranism back with a live video for you. It is a first ever debatism. It's debating my way, I guess you could say. This was born out of dissatisfaction with most debates in that they are too long, in that they are not structured, and they really have no rhyme or reason. And so what I wanted to do is present something a little bit more succinct. We're going to try and get you guys out of here in 90 minutes, which would put us at what, say 6:15? So 7:45, we should be done if we stick to the schedule, which I believe we're going to do. Let me bring on the guys. But by the way, I should probably show you what we're doing tonight. It is episode number 1 of Debatism. MCToon against Brian Leake. The shape of the earth is the topic. Let's go ahead and bring them on. We've got the clock ready. We've got both guys here. Let me take them off mute since I muted them because they were talking in the intro. That was fun. And yeah, we're ready to go pretty much. Just to show you across the top of the screen so that you can kind of follow along with where we're at. We're just going to do a quick welcome. We're in the middle of that. We're going to do intros, which will be 2 minutes each. Then we're going to do questions, which each of them has prepared 3 questions for the other one. So we'll go back and forth on that one with questions. That might be a problem. And then we'll do topics where they each are bringing 6 topics to the table. The way the topics work, they'll just bring it up. Basically, whoever's topic it is will say, hey, let's talk about this, and this is what I think, or whatever. And then we'll get 5 minutes clock running on that one. And then we'll go to conclusions, 2 minutes each. And then if there's any super chats, we'll do those last. So let's flip a coin. Is that going to be a problem? It is a little bit. 1 second. I got to shrink this screen. Damn, that's going to be a problem. All right, let's put it over here. I'm going to do a coin toss. And who wants to call it?
Heads.
Okay, well, that's Brian's calling it. So let me get over here. And can you guys see? No, you can't see it there. We'll put it over here. All right. There we go. And I just want to be able for you guys to see it. And that's not going to work there. All right, we're going to cover MCToon for a second just because it's fun. All right, and then we're going to flip. Here we go. And he called heads. It is. It is tails. So, Toon, you want to go first or you want to go last?
I'll go last.
Okay, that means you're up first, Brian. Go ahead whenever you're ready. You're doing your 2-minute intro, and you're up.
Okay. All right, give me 30 seconds, man, because since this is the first show, I want to, give a shout out to you.
Oh, thank you.
I want to say thank you. I feel like, you're filling a hole that's been left since a long time ago when the Flat Earth Debate channel started. And then I guess Ranty kind of filled that void. Ranty begat Nathan, and then Brandon begat Ranty, and now you begat Brandon. So, you know, a sizable, I want to say a flat earth channel, you know, that's respectable in size. No disrespect to any of the other debate shows, but a YouTube channel. So we appreciate that. I think Globers and flat earthers alike trust you, and hopefully me and Toon will set the pace. I just want to ask him to keep it as honest as possible. I'm not going to try and bring an ego. I think if Craig is willing to submit to a point period, then we should be able to, and everybody should be able to. If he can humble himself, then Jaron and Craig kind of set the standard. So I'm just going to ask for demonstrations. I know you like numbers, and you know me, I like demonstrations. So that's what I'm going to be asking for. But I'm gonna just keep it real, and this way we can police our own the way we used to.
Let's do it.
Yeah, we can police our own. And all right, that's
ready?
it. I'll pass it.
That's your intro? That was quick. All right.
Yeah.
Good. All right, MCToon, you're up. Your 2-minute intro. Go ahead.
Hey, thank you for setting this up, Jaron. We'll see how this goes. I think it's an interesting idea, and I'm glad to be able to be on the first run of it.
Yeah, let's try it. It could be an evolving thing. We'll see how it goes. But I think I like it structured. I like it. And I think people will learn a lot from each debate. In 90 minutes, you're going to get, like I said, 12 topics, 3 questions each. You'll at least walk away with understanding what both these guys' opinions are and positions. So let's see here, Brian, you're up first, and you get to ask Toon your first question.
Yeah, Michael. So my first question is here just north of where they launched, in Jacksonville, Florida. They some people, me, I've actually tricked some people and pointed, since I learned perspective, I pointed to the horizon, when on a clear day when you could see an airplane fairly close to the horizon, and said, "Look at this space shuttle, check it out." And they was like, "No kidding, man. It literally looks like a space shuttle on a clear day where you could see that far going straight up for a couple minutes." I'd like to ask, how do you explain that in your model? Why does the airplane look like a space shuttle in the distance going straight up in the air? And then when it gets overhead, it gets straight. And then as it sets on the other horizon, it looks like something going directly straight down. How do you explain our local, sphere of vision, for lack of a better word?
Well, it's not a sphere of vision, but how do I explain that? That is simple perspective. Every single part of the path that plane is taking can be explained easily with just solving triangles. And if you don't need to know anymore the actual process of doing it. There are online calculators for it. So when an airplane is, say, I don't know how far away you can actually see an airplane, but let's say it's 20 miles, right? So when an airplane is 20 miles away from you and it's 6 miles up, right? Then you can solve a triangle, and you're going to say that is a very low angle, very small angle to the ground. When it's closer, say it's 10 miles away, that angle is going to be higher. When it's directly above you, well, of course, it's going to be straight up. And then as it passes over you, it's going to reverse that same line of that it did on the way there. And so that angle is going to progressively get smaller. So it is a simple application of a perspective, solving triangles. It's taught in middle school. In high school, typically you're taught to do it with actual sine, cosine, tangent. So.
Right, real quick. I know we're going to jump topics, but real quick, it definitely, my whole point in saying that, maybe I should have specified, was that it doesn't appear linear, and you don't see it, 20, maybe 25 degrees.
It's not linear. It's not linear.
Right.
It's an asymptotic relationship.
Right. So it's a squared relationship, or whatever you want to call it, but it's pretty much. You said perspective can.
No, it's not. It's not squared.
If perspective could describe it, then we'd see it coming up over the horizon at 1 degree. That's not the case. We see it at about 18 to maybe 25, depending on how clear of a day it is. And for the first couple minutes, it literally appears like it's going straight up. So it's definitely nothing about it's linear, or logarithm or anything you want to call it. I'll give some examples.
Hold on.
That's okay.
Let me be clear.
Go ahead.
We've gone off track already here,
Yes.
but it's okay. I don't care. But I gave you the answer. It's not squared. It's not logarithmic. It's asymptotic. That's the word you're looking for.
Okay, you're
Use
going
that
with your question, Toon.
All right. My question. What is the bottom-up obstruction prediction formula for flat Earth?
Non-existent? No, I'm just kidding. I'm going to say, well, there's a couple ways really to do this, man. The first way we do is get the distance to the horizon. So I think what Toon's looking for, and like I said, I'm going to try and keep this as honest as possible, is that 8 inches per mile squared is the measurement of the Earth, but has nothing to do with the hidden obstruction. So I'm going to try and keep it real. And what he's looking for is the formula. So, you can you have to start with the distance to the horizon, which is one way to do it is 1.22 times the square root of the observer's height in feet. And then you take that and then you apply, let me see, I wrote it down. So X would equal, A squared minus 2AD, where A is the obstructed height and D is the distance to the object, plus D squared plus R squared minus R. So basically, but you could also do it, I've seen a couple things where you could do R plus H, where R is the radius. And I actually tried this and it does actually work. It didn't look like it worked, but R plus H, which is the radius plus the viewer height squared minus the radius of Earth squared in feet, and all that square rooted. It actually does work if you do these numbers. But the real way that most people would do it too was I would say it'd be like it'd be G over O to the OGL times E. That's the way most people do it, where G equals Google, and then the OO equals Earth curve calculator, and then the LE, of course, is type in your height and your distance, man. So that's how most people do it. I'm just joking, man.
Okay, your question, Brian. Go ahead.
All right. So number two is.
All right, hold on, Jaron. Write this down for next time. You need to give one like quick answer back.
Okay, we can do that
next one. Yeah.
We'll do that. Do you want to give your answer? Well, we'll do it next time. Go ahead.
Yeah, absolutely.
I just say all that was based on the globe. But okay, go ahead, Brian.
No, go ahead and respond to that. Was that what you was looking for, though? Like the 8 inches per mile squared is?
I was looking for the flat Earth formula, not for the globe formula. You gave me the globe formula.
Oh shit! If you want a flat Earth formula,
yes, that was the question. It included 4 flat Earth in the question.
For flat Earth.
Brian, you goofball! You goofball!
Bro, it didn't say nothing about flat Earth, because I've already gave you my formula. It's 90 minus A over 90 times D times point A times 100 of A minus 1/2 A, where D is the triangulated distance to the sun or star, whatever you're measuring.
This is the bottom-up obstruction.
Yeah,
when something is 40 miles away, how much will be obstructed? Oh my gosh!
Ask your question, Brian. Go to the next one.
I'll tell you what. I put in a 30-second video to explain this, bro. I thought we were gonna be honest. You're a veteran. I consider you a veteran, but if I got to re-show you this, I got a 30-second video for anybody who doesn't understand how the sun sets on the flat Earth.
I didn't ask how the sun sets.
No, we're not gonna. We're gonna go to the next. No. You ask your question now. We'll pass that one. Brian, you're up.
Well, you interrupted me during my formula, so I'm just saying. He's what exactly are you asking for, man?
He
You
was
don't want my
he was
formula.
looking for the bottom up obstruction equation for a flat Earth, but let's move on to the next one. This is what I didn't want to do, is get stuck on something. He didn't. That's fine. We didn't get an answer for that.
What
It
does
doesn't matter.
What does he think? Wait. What does he think I was giving him? Just like
You gave me the globe formula.
no, I didn't give you the globe formula. 90 minus A over 90 times D times point A times 1/2 A is not the globe formula, bud.
What's that formula do?
I'm sure that's a refraction formula. Like I said, every flat earther might not agree with this, but this is just a pretty much a distance formula. And then from there, you figure the obstruction.
Okay,
By doing
when you get,
two
we can do this in the
times
topics if you want,
that.
but move on to your next question,
Yeah.
Brian. Please, thank you.
Okay. Yeah, I'm not trying to not answer questions, just so y'all know.
Gotcha.
So, hold on a second, man. 1 second.
Yep. What are we on? His second one?
It's yes.
Did I say 90 minutes? I meant 190 minutes.
You gotta love Brian. He's always Brian. He's always the same. You gotta love him.
Sorry, we'll get you the question here eventually.
He just like, oh, just a second. And he walks away.
Yeah, I don't, man. I'm sorry, man.
It's okay. We're ready.
Sorry about that.
It's so good.
Okay, number 2, man.
Yes.
Number 2 is, let's say, how would you, with an auto level, pushing it to its limit, pushing it to about, let's say, 100, 150 yards per shot, how would you lay out a straight line?
All right. Let me read what I was sent, just because I answered what was sent to me. If level is curved, using an auto level and pushing the distance limits of 100 yards per shot, how would you lay out a straight line on land 1 mile long, your choice of elevation? My answer is I would hire a professional surveyor that has experience doing it and knows how and knows the process, and ask them to plot out a 1 mile level line at constant elevation. Then either myself or, if the budget allows, ask them to also do a calculated elevation above that, based on the globe known radius and how much it should be above that to be tangent to that point. So, for example, at 1/4 of a mile, which is 4.5 football fields, the second point would be 1/2 of an inch above that measured level. At 1/2 of a mile, it'd be all of 2 inches, and at a full mile out, it would be 8 inches above the level line. Now, the difficulty is how would you, from a whole mile away, see that 8 inches elevation change and just eye it and know how it's useful? I don't know how that could be useful. But at least it's a little better version than Brian Mullen's goofy thing where he thinks that he can build a perfectly rigid structure.
So to get this straight, you would lay out your straight line, and you said you would raise above your horizontal 2 inches.
No, you got in the first sentence. You got it wrong. I would hire somebody that has experience doing it to lay out a level line, not a straight line. Level is a curve on the surface of the globe.
No. That's why I asked specifically for a straight line, because they're going to give you the same thing. You can tell them level or straight.
I gave you the answer. Well, I'll give you the answer again. Step 1: hire a professional surveyor.
We don't need to repeat it. We don't need to repeat it. He can go back.
Lines.
He can go back and watch it again if he didn't hear it the first time.
All right.
So go ahead. Your question number 2.
All right. How far away does the sun need to be to set over flat Earth?
Okay, now you said flat Earth, okay? There's nothing about flat Earth. You're sitting there mucking with me and shit, and it says nothing about flat Earth in your first question. Nothing at all about flat Earth. It says, what's the Earth curve? What's the formula for hidden height? There's no hidden height on a flat Earth as far as obstruction goes, you know. But anyway, I was trying to give you a formula. And anyway, so
Okay, go.
I'm gonna refer to the way you answered as just is there is no obstruction.
So you're saying the sun never sets.
The sun sets. You're gonna use Jaron. I don't even want to just play my FE sunset video.
Okay. We're going to play this, and we still have the clock going. FE sunsets. All right, here it comes.
Yeah. So, in case anybody hadn't seen this, I figured he's a veteran. And this is a white light and a green light about over 100 feet, and the door just closed to a warehouse. And letting cold air in, and the white light disappears right in front of the camera. And then the green light disappears. Now, here's the way they describe refraction. It ain't quite, I'm not seeing shit raising up. This is the sugar tank experiment. But for anybody who hadn't seen it, with just atmospheric lensing or magnification, you have the sun dropping and setting and not changing size. So I thought we was going to keep this honest. But you see the sun setting right in front of the camera, not change size on a flat Earth. There's two ways that can happen, dude, with just cold air, with just a little magnification in the atmosphere. I see where this thing's going already, man. So I'm going to act accordingly, man.
Yeah, I have a question. So then you're saying that the sun is literally on the ground? Because in this demonstration, the sun, your analog sun is literally on the ground here. So you're saying that the sun is literally touching the ground in reality?
Nope. Did the sun touch the ground? Did the sun touch the ground in either example?
Yeah, and your analog is right on the ground there. So, okay.
No, I'm saying, did it actually touch the ground, though, in either example?
But, yeah, it sure looked like it was.
Did it reach zero when it was just sitting above the ground in front of the camera?
Yeah, it looked like your analog setup that you had there had the sun right on the ground.
Did it ever hit zero?
Did whatever hit zero?
Did whatever hit zero? Did either example approach zero?
Did what approach zero?
The sun examples, the white light in the first video, or the picture of the sun, or the flashlight in the second video. Did either of them touch the ground or zero? The horizon is zero.
Yeah, it sure looked like you had placed the light, or whoever had done it had placed the light right on the ground.
Like it, yeah. But it didn't, though, right? It didn't, though. But it did disappear, though, right?
Yeah. So what I'm getting is that you think that the sun is literally basically right on the ground for flat Earth. That's what I'm getting.
What I'm getting is that the sun right in front of your direct line of sight disappeared. There's two examples of how it could work on a flat Earth, plain as day, without the size changing on top of that.
Okay, let's go to step one. Step one, put the sun on the ground. Step two, it disappears.
Above zero.
Okay, we got it. We got above zero. What's the who's up? Brian, I think you're asking your third.
No, I think it's his okay, if it's my third question, okay. My third question is okay, so how in your model, and I know you have an explanation, man. Let's settle back down, Toon, man. I ain't trying to get all shitty, man. I really ain't. I'm sorry I misinterpreted the first question. It threw me off a little bit, man, but let's keep this real, dude. I mean,
okay, ask the next one.
So next question is, so how would you explain in your model, what would it take for the crosshair to block half a mountain and appear below the water horizon, as exampled by myself and by George Nowczek's Ice Lake measurement, and by Jessica Kozlowski and Tim Osmond's Great Salt Lake Strong's Knob measurements at like 7 foot above the Great Salt Lake. So it's not that rare. But how does the globe model explain that?
So to be clear, you're saying that I'm not familiar with your particular example for you, and I didn't look up Jesse and Tim's. I have seen George Nowczek's thing. So you're saying, what you're asking is, how is it that if you're several feet above the water, that the crosshairs can be below the horizon, right?
Right. So we don't see in perspective the way you was trying to pass it off earlier, right?
No, yeah. So the way, and I mean, this is a great example. So when light goes through a gradient, a pressure or temperature gradient, it curves, and that curve has a radius. If that radius is larger than the radius of the Earth, then it will make something appear slightly higher. If that radius is smaller than the radius of the Earth, then it can cause distant objects to appear higher, significantly higher. So, for example, the horizon can appear higher. And I personally measured in March of this year, I went with this NIST certified thermometer to a lake near me, and I measured the vertical temperature gradient. And at 1 to 1.5 meters, it was a full degree Celsius temperature change. For the radius of the curve of the light to be the same as the radius of the Earth, you need 1 degree in 10 meters. And this was significantly less than 10 meters. So that's causing the arc of the light ray to bend significantly more. So that's how you can see things above the crosshairs, is because refraction can raise things that much in certain conditions. And so, for example, George Natchick's Lake example is a great one, because like I did, we know that at the bottom portion near the surface of the lake, that temperature gradient is pretty steep.
Okay, MCToon, your third.
Right.
All right, my third one. What is the derivative of x squared with respect to x?
I mean, I'll give a couple different answers because I didn't seem like enough information, but the basic answer would be 2x or 1 over x squared. Or if
2x.
you want to, if you want to take it a little bit further, though, if we're talking about derivatives, just for anybody who doesn't know, I'll make it just quick, Jaron.
Mm-hmm.
Is where you're talking about the change. Basically, when we talk about it, we're talking about the change in the slope, like to a tangent or something like that. So if you want to say, if you want to give it a value, like if it ain't squared, that means it's a constant, which means it's a straight line. So we could just use rise over run, right? But if it's if you want to give it a limit, that's why I was kind of expecting something harder, like a limit. Like if you gave me 2, I'd say as 0 approaches 2, then I could have done something with it. It was so simple. I thought he was trying to trick me, but I don't know.
It's not a trick question.
Right. I don't know.
It's really just 2x.
Right. 2x.
That's all you had to say.
Okay, so we are good. Everybody asked all 3 questions, yeah?
Yes.
Okay, so Brian, you get to name the first topic. Go ahead and make a little, small, short 30-second statement, and then we're going to have a back and forth. If it goes well, we'll keep doing it. If not, I'm going to move it to 250 each, or 230 each, 2.5 minutes each. But for now, we'll start with open conversation with your first topic. Go ahead, Brian.
Okay. Let's see. My first one, I'm going to say, I wanted to see some demonstrations for the way you were just describing that radius, with the refraction. Like a demonstration would be nice. I showed the fish tank demonstration and how that works for a flat Earth. If you could show me refraction demonstration for a globe, or if you could just explain the radius, the way you just described it, as applied to that white light on the warehouse floor. If you could apply that explanation to that white light that's about 3 inches above the floor in line of sight, that would suffice. Or any demonstration.
So in this part, where I thought you were going to be bringing something, you're asking me to bring something?
Well,
he brought the topic, so
you just brought the topic.
Light.
Okay.
And yeah.
Yeah, I didn't prepare anything.
I
prepared 6 things for my topic. I got links and web pages and stuff to show. So I don't have...
Well, show me a demonstration, or just explain a demonstration of refraction.
Yeah, maybe you could explain it.
All right. So if you I'll give you a little more detail in the temperature gradient there. So you can read about this on I don't remember the name of the page, but it's from Andrew Thomas Young at San Diego State University. It's some really good description of how this happens and links to different papers analyzing it. And then I have on my website at mctoon.net/refraction a list of empirical measurements of the temperature gradient and different conditions. So some have gradients measured, some have conditions identified. And then the actual amount of change in elevation that something appears to have because of that temperature differential stack, right? So the critical number is that the radius of the arc of light is equal to the measured radius of the Earth when there is a 1 degree per 10 meters change in the temperature. And this is Celsius.
Can you demonstrate that?
Can I demonstrate? Yes. MCToon.net/refraction. There's a handful of different measurements of it. And there's specifically, I can tell you the name of the one. I mean, it's just a paper and they're going over the details. So it's not something interesting to go to look at right now, but I can tell you the name of that one at least, and you can look it up. It's on my page. I have a list of things I've read and then a list of other things I have not read. So this is the final one that I have read. It's called Results of Leveling Refraction Tests by the National Geodetic Survey. So they took a bunch of
no demonstration. Gotcha. No demonstration.
Correct.
Excellent.
I did not prepare it.
I didn't bring one
for
because
you, Brian.
You're supposed to bring up a topic, and then so he.
I'm messing with him, man.
Okay, good.
So they took a handful of Invar bars, and then they stacked. I mean, I can share my screen here. You can have a look. There you go. Can you see? If I share that, do you see it?
Yep.
All right, hold on. I gotta fix it on my side because people aren't seeing anything on my side at all.
Tell them just tune into the better channel. Turn to my channel. They can watch it there.
What? Hold on a second. I do like that you said tune in.
I forgot to mention it's Tuesday night, isn't it?
It is Tuesday night. Crud! I screwed up everything over here.
Sorry, we've kind of gone off the rails already, so it's all right.
We yes, that's the case. Oh my goodness. Hold on. People, you're seeing.
So by the way, I'll let you do that while I tell people real quick. If people want to, you can go to, the best place to reach out to me if you're interested in debating, if you want to come on the show, reach out to me on Telegram, t.me/jeranism. If you have no opponent, just message me and say, hey, I want to debate 5G or whatever it is. And then I'll put your name on my website. You can go to my website at jeranism.com/debate. It's not quite ready yet. It doesn't have anybody's names yet, but it does have a couple things people have said they want to debate and they're looking for opponents. Or the easiest method would be to already have your opponent, in which case you just message me on Telegram, say, hey, me and Jim are going to want to debate this, and then we will get it scheduled, and then you'll be on the show. So it's that easy. And bring your debate here if you'd like to get it over with quickly. And yeah, these guys did exchange all these things beforehand, but you can do it either way. Either you guys can decide to exchange questions and topics beforehand, or you can do it blind, up to you. Toon, you ready?
Jeremiah?
I am ready.
Okay, go ahead.
All right. So here's an example of their setup here. They have these bars. These are Invar bars, which is a particular type of metal that is very resistant to changing length and size due to temperature. And here is the stack of the temperature sensors reading the different temperatures above the ground there. So that's the really important thing of what they were doing. Then they did this. They set up this network. They measured the difference in elevation due to at these different locations. And yeah, that's the interesting stuff. So anyway, that particular paper is a real good one to look at if you're actually interested in like seeing how they do a controlled test of what it looks like, what refraction does in the air. So
okay,
that's a demonstration.
Topic 1 for you, Toon.
All right, hold on. I gotta fix this now.
It's okay.
Hey, Jared, while he's fixing that, will you look at that first question, man, and see if I will. It mentioned flat Earth?
I don't remember what it was, so I'll check it.
I did not include flat Earth in the wording.
Okay. So there's your answer.
So
so you by default win the debate, all right? You have it now, Brian?
Well, you can't win them all, dude.
Well, I mean, I kind of have already. So I mean,
Well, now you got an L on the
it's-
record.
Well, I started off
Yeah.
saying I wanted to keep it honest, and I'm sitting there answering something you didn't even ask, and I apologize for that. But no, now I don't. Now I don't apologize. No.
all right,
I'm just
all right.
kidding.
I fixed everything. I'm back to normal, and now it's my turn. You know what? I should have just left it because I need to show something because I brought stuff, Brian. I brought stuff, but all right, that's fine. I will share it.
Okay.
Yes, there we go. All right, here we go. Here goes my topic. This is, hey, you know that guy.
You're inside your airplane, and you just like, oh yeah, see the curvature? Yeah, I see it. Fine, take a picture of it, put it back on your whatever screen, hold up some sort of straight edge to it, like this thing right here, hold up straight edge to it, and tell me if it's still flat. If it is, great. Send me that picture. I will quit Flat Earth tomorrow, and you'll be famous for getting me to just ditch Flat Earth.
There you go. So I did exactly that. I sent 4 of them to Mark Sargent. I'll just cover them now. And Mark isn't here. Brian, you don't speak for Mark, so I'm just going to show what I sent to Mark. So here is a picture of the horizon from an airplane at 46,000 feet. Here it is at the top of the screen. Here it is at the bottom of the screen, showing that it's not fisheye lens or a heavy distortion of the lens. Could it be the cockpit?
I want you to.
It can't be the cockpit because this was from Wolfie. He found in his hangar there, he's got this bar that's curved, and he's got this bar at the bottom that's straight. And he went inside of his plane, and inside his plane through that very same cockpit, that curved line appears curved, the straight line appears straight. So we have a strong control there. Curves lines are still curved and straight lines are still straight. So it can't be that it's being manufactured by the lens or the canopy. And then to further one more step, hold on, I'm almost there. One more step.
Yeah,
Walter Bislin analyzed based on the elevation and the camera, the specifics of the camera. He analyzed the globe prediction for how much curve you should see. And this is it here. They match right on there. So the predicted curve for the globe and the visible curve match when accounting for the specifics of the camera. So, all right, there you go.
Okay. Well, one of my questions or one of my topics was compressed horizon curvature. So if it's okay with Jared, I'll just make a quick comment to defend Mark Sargent, and we can speed it up because it pertains to this exact thing. If that's okay, I was going to say that would you agree? If I'm going to defend Mark, would you agree that he's asking for Earth curve?
Yes.
Right. And would you call that Earth curve?
100%.
Why is it showing straight and then it's showing curve? But so if I'm looking straight out in front of me in that airplane, at a level horizon, so we're not talking fisheye lenses, we're not talking about mountains on one side, we're talking about a fairly even horizon, in all fairness. And so you would agree that if it's 4 degrees straight ahead, then off to the right, it's also going to be 4 degrees, and then off to the left, it's going to be 4 degrees. And then if I turn around, it's going to be 4 degrees. As long as the horizon, the landscape is relatively level, I'm going to have a 4-degree drop no matter what I'm on, fall, flat, whether you compress it, whatever the case, right? So not Earth curve.
I have no idea what you're talking about. I showed you the predicted Earth curve that Walter Bislin did, and it matched what was seen from the airplane. So I don't know exactly what you're talking about with this 4-degree thing.
Well, my question is if I have a level horizon, every direction I look, whether it be globe, flat, is going to be the same degree drop every direction I look, right?
Well, that was not. I wasn't showing the linear drop. I wasn't showing the dip in that one. I was showing the left right curve in that one. So it's a different topic.
You'd agree that off to the right, if it's 4 degrees straight in front of me, off to the right, it's also 4 degrees.
What is 4 degrees measuring, Brian?
This drop you're talking about, okay, or the drop we can measure, we could call it 2 degrees, whatever you want to call it. It's an arbitrary number because it does change constantly. So my point is if I look straight out ahead and I can see 200 miles and it's a 2 degree drop, if I look to the right, I'm also going to see 200 miles and a 2 degree drop. And if I look behind me, I'm going to see 200 miles and a 2 degree drop. Even if the Earth's a globe, I'm not going to see Earth curvature. I'm going to see the same degree drop every direction I look. Right?
Why are you talking about the linear drop? I'm showing a curved horizon.
How many degrees of curvature is it then? So let's say it's 2 degrees straight out in front of me. What is it to the right and left?
Why won't you stay on topic?
I'm
showing the left to right curve.
I'm asking you to explain it in degrees.
No, I'm explaining to you that Walter Bislin did a specific prediction of what it should look like for the globe, and it's not a 2 degree something. It's the left to right curve that you should see on the globe, and you're talking about the linear dip.
Okay, Brian, go ahead. You're up next. Your topic.
Yeah, that's tough. Okay, so I wanted to say 2 things. Okay, I didn't bring the video for all this, but I'll explain it. So a helium balloon in a vacuum. Okay, a couple things. Okay, they say that, that it's pretty much, they say gas has mass, so it's attracted to the Earth. And we claim that, no, it's not. Like, even a helium balloon in a vacuum, you got to use a real tough balloon, but Action Lab pulled it off, and he used some real strong water balloons, and he was able to get a couple of them not to pop. And so as the pressure decreases in the vacuum chamber, that increases the pressure in the helium balloon. And so it hits a point where it can't support the weight of the balloon anymore, and it kind of drops down. It doesn't like fall at free fall, but and he shows how much air is left in there, and it's about enough to fill a size of a quarter. And so my question would be this. Well, 2 questions. One, shouldn't it, if the buoyancy equations are accurate, shouldn't it have kind of eased down? Shouldn't it have hit a point where it was like halfway the way we see it in air? And number 2, can you justify the amount of that tiny bit of amount of air left in there for it to ever fall at the same speed as a lead ball? In other words, in my opinion, it'll never, if I drop a lead ball in a vacuum chamber in that helium balloon, it's not even going to be a contest. The helium balloon is going to ease down and the lead ball is going to haul ass down. Is there enough air, that tiny bit of air left in that vacuum chamber? You think it's enough to justify that slow rate?
All right. So you have guessed that in a vacuum chamber, you guessed that a helium balloon would not fall at the same rate as something that was much more dense. I'm going to say I'm going to need more than your guess, but yes, in an evacuated chamber, a helium balloon is no longer buoyant, so will fall. And Action Lab did a good job there. I'd like to see it done with a Mylar balloon, because that they don't stretch like latex or other balloons like that. So I don't quite know what you're talking about. Things still fall. Helium balloons still fall in a vacuum chamber. They lose their buoyancy, and so yeah, when you do the math, you actually apply the buoyancy formula. You do find that helium balloons do what are predicted in a gravitational field.
Okay.
Any other questions on that one? Or
we don't have time in our 3 minutes to
so your answer
explore
is
the
that
formula.
little bit of air left with that little bit of air is enough to slow it down where it doesn't fall at free fall speed. That's fair enough.
No, hold on. Don't put words in my mouth. What little bit of air? The little bit of air in the balloon or the little bit of air in the vacuum chamber?
You've seen it. I'm not trying to put words in your mouth. I'm saying that that you agreed with the buoyancy equations.
You didn't answer my question.
Well, Bryant Myers said that he said that up high things. He said he was thinking strictly math, and he said things should fall faster up high because there's less atmospheric pressure. But he said that ain't the way it works in the real world. He said that when he was debating Austin, and I played it in Globebusters a few Sundays ago. And but he's wrong. Wouldn't you agree that things absolutely do fall faster up higher due to the fact there's less air pressure?
You've brought another thing into it here, though. You've brought wind resistance into it. Right? It's no longer just buoyancy gravity. It's now buoyancy gravity wind resistance. So when you're at high elevation, there's less air, there's less wind resistance. So your velocity can be higher.
I'll tell you what, I'll send you a clip, and if what I'm saying is accurate, which I believe it to be, then you could correct him on that. I'll talk to Mark Sargent, and you talk to Bryant Myers on that one.
Yeah. Look at us getting things done.
Things do fall faster up at altitude, according to let's say the Red Bull jump.
Because of wind resistance, not buoyancy.
Yeah,
it's a change in wind resistance.
Right. He said that you would expect that to happen due to wind resistance, but he said that we don't. He said that we don't, and I disagree. And I think you do too.
Okay, Toon, I think you're up.
All right, I'm going to share my screen. I have a $10,000 gravity challenge that I've more recently than the other challenge that you might have heard of, issued. This was actually this is my very first challenge. I issued this with the money that I won from Flat Out Hero, but this is now backed by my own Bitcoin. The challenge is to beat gravity at its own game, and to predict the specific magnitude of the downward acceleration for different areas on the Earth, because we know that the value changes. It's about 9.8 meters per second squared, but it's not exact, and it varies from 9.7 to almost 9.8 depending on location. So I have that challenge there on my website, and I have how I actually do my prediction for the globe. So all you need to do is you provide the mechanism for that and how to predict the specific amount. And you do that for 5 locations, IGSN locations. They've already been measured. You don't have to go do anything. You send them to me along with the formula. I'll pick 5 IGSN measurements, and whoever has the smallest error out of those 10 wins. If you're right, you win 10,000. If you're wrong, you lose nothing. So I use the law of gravitation formula there, and I use the second law of motion there, and I give specific places where I've done examples for how I've done it. So right here we have Kauai, Hawaii, where it's 9.787, and here Fortaleza, Brazil, which was where one of the Eddington party went in 1919. It wasn't Eddington, it was Campbell, I think. Anyway, and Fortaleza, Brazil, there you go, 9.78, and then up in International Falls near me, 9.808. So those are the measured amount, and here's the predicted amount. So the predicted amount and measured amount is very close. There's the actual amount that it's off. So all you need to do is do that for whatever you think causes things to go down, and do it better than gravity. You win 10,000.
Okay.
What do you think?
Well, I sent Jaron something to play, but instead of that, I'm just gonna give a brief description of it, and that's cool. You put your money up, but to be honest, I'd like the way you formulated that challenge, like you pitted it against literal nations worth of data and stuff, and you said that we can't use kinematic equations. Okay, so we have to come up with a cause, but we can't use mass or any form of mass or any constant. And I'm thinking,
well, no, you can use a constant. You just have to show the derivation of the constant.
Fair enough. Okay. Well, ain't that oxymoron kind of? But no, I see what you're saying. But so you want to see, the cause explained? So I want to put you through your own challenge. What's the cause in your model? And this law of gravity you speak of, are you speaking of Newton's law, m1 times m2 over r squared?
Yeah,
And you're
I had
using
it.
the g constant?
Yeah, I had it on the screen there. Yeah.
So so Newton knew the constant then, right? Since it was a law, Newton must have knew.
No,
The
Newton
constant.
did not know the constant. No, he just put together the formula.
So he just copied the Coulomb's law then. And then later on, 100 years
hold on a
later,
sec.
they came up
Brian,
with the constant.
Brian, Coulomb was born after
It was
Newton
10
wrote
years
published.
before.
Coulomb,
It was 10 years before.
what was 10 years before?
Coulomb came before the law of gravity.
Oh, are
Yeah.
you sure about that, Brian?
Yeah. Can you tell me who came up with Big G?
Hold
Wasn't
on.
Newton, was it?
Hold on, you didn't change. You changed the topic there. All right, let's look at.
Are you talking about just the formula? Or are we talking about Big G? And what a Coulomb is? And
I'm
what
talking about the
constant is?
law of gravitational attraction.
So it's Big G
Uh-huh.
times m1 times m2 over r squared, right?
Yes.
So
yeah.
so Big G, wasn't that Reverend Michel and Cavendish?
Well,
Or
Cavendish
was it
is credited as the first one to measure Big G, but Newton
So
came
all
up with the
Newton gave-
law long before Cavendish.
How can he have a law if he doesn't even have the full equation?
He had the full equation. He just
he
didn't
didn't
have the
have
value
Big G.
for one of the variables.
So he had basically Coulomb's law without the constant, without the electrostatic constant.
But I don't know why you're bringing Coulomb's law into this. Coulomb's law came after.
You are saying that.
Why are you?
Newton-
Hold on, Brian. Brian, I just want to make it really clear. It's not possible that Newton copied Coulomb's law because Coulomb's law came after Newton.
What's Newton's law? If he doesn't
F
have the value for G,
equals G m1
He didn't
m2
have
over
G.
r squared. He
Don't
didn't
just
have
throw
to
in
have
G.
it to create the
F
law.
G. So he just had an equation that
Yes.
matched
Yes.
Coulomb's law without the constant, right?
It was before Coulomb, Brian.
He didn't have Big G. What are you talking about? Is before Coulomb. He didn't have a constant, period. You can't have a law if you don't have the equation.
Yes, you.
Dude,
Yeah,
so
yeah. You actually
I
can.
can invent a law right now and just give a squared function, and I've invented a law.
You could, and then people would test it and see if it works. And if it doesn't work, they'd say that didn't work. So sorry.
Okay. So,
Okay.
Yeah, anybody can come up with any hypothesis they want. Any day they can chuck stuff out there all day long. And as Feynman said, you can guess. A guess is a perfectly fine way to come up with a hypothesis.
Well, you at least concede that Newton couldn't apply his law.
He did apply it. He derived it from Kepler's laws.
But he couldn't apply it because he didn't have Big G.
He didn't have, but there's other ways that he worked through these things.
But in your challenge, we can't use them. We can't use anything kinematic. We have to come up with a constant and all that stuff. But my point is that Newton, you keep calling it Newton's law of gravity.
It's not me that coined that phrase. That's been the name for centuries.
Police your own, please.
Well, they're correct. It's the name, and it is the name, and it's correct because nobody's found it to be wrong yet.
Nobody give a cause.
That's not how you test a law. You test a law by seeing if it works. You don't need to know the cause for a law to be a law.
But in your challenge, you want us to tell you a cause. So I would.
Yeah, you're proposing something else.
Cause. Well, I'm asking you, what's your cause?
Mass attracting mass. Yeah, mass attracting mass.
Okay, that's dead. Okay, that's not instantaneous, is it?
It doesn't change anything. It's not been found to be wrong. This is your opportunity to get paid.
So we don't need
be
Big
better
G
than
then. So I don't need Big G then.
Of
right?
course, you
use
could not be
kinematic
using.
equation.
You could not be using big G because that's gravity's thing. You are proposing something other than gravity. So why would you want to use gravity to disprove gravity? That
So
seems a little self-defeating.
You admit Cavendish had almost a century to look at the equation and retrofit the constant.
He had almost a century?
Yeah, to retrofit big G.
What do you mean to retrofit big G? He measured things.
You can't come up with big G if you don't have mass or a certain volume.
But I'm not asking, Brian, I'm not asking you to produce big G. I'm asking you to produce the downward acceleration, a completely different thing.
Okay, let's go to the next topic.
So you don't need to. All right.
Who's
so you
up?
don't need a code. Okay. This is fun.
I got to keep
All right,
better track of who's up. Is it Brian?
Yeah,
Brian,
yeah.
read it again because you're not. I think you're confused about what I'm asking for.
Well, you call it a law of gravity, and I've got a problem with that. I think you should.
Then disprove it by producing the other thing. Oh, you don't need to worry about what I'm doing. You need to worry about what you think is causing the downward acceleration.
Like I said, I'm trying to get this everything honest and everything, but anyway, I'll go through with it. So locally lit clouds. I must say that in the heliocentric model, the sun is supposed to be 93 million miles away. Yet with the sun and the moon, we see locally lit clouds. We see hot spots with where there's no water around. And one of my main points is that it was thrown at me that the sun putting a shadow up on the bottom of clouds or lighting up the bottom of clouds was some kind of proof for a globe. When in my earlier I showed how it works just with atmospheric lensing, but if we're going to use the trigonometry, if a sun is 1 degree above the horizon, that means it's 1,600,000 feet approximately. I mean 1,600,000 miles above the tangent of my feet toward the horizon. So it's way above the clouds. So if a sun, I've showed several, but I've showed the sun up to like 4 or 5 degrees, still lighting up the bottom of clouds. Now, how can a sun that's millions of miles above that cloud be casting light on the bottom of that cloud? How's that possible?
Because it's not millions of miles above that cloud. That's easy.
Okay. So you disagree with the trig that a sun 1 degree above the horizon, okay, 93 million miles away, puts the opposite side at 1,600,000 miles. You disagree with the simple trig?
You did not show any trig, so I'm not going to agree or disagree to any trig that you're referencing. I've not seen it to agree or disagree with it.
All right, I can pull it real quick. Oh, wow.
I can draw a diagram. To show.
Put in 1 degree.
No, I'm not putting in a degree. I'll just draw a diagram here. And it's not to scale.
Well, in your mind, you should know it's going to be well closer over 1 million, just from the numbers themselves.
All right. Here you go. Here's that's the Earth there, right there. There's the Earth. There's the sun off page there, right? And here it is coming up to hit the bottom of the clouds. See that? That's pretty good. I even used a straight edge for that. Now that works pretty well. But here's what I don't get. How high is the highest normal cloud, Brian?
I don't know, a few miles maybe.
About 6 miles.
Why are you failing to answer questions? Do you disagree that that 93 million miles distance, the height of the sun, 1 degree above the horizon, would be roughly 1,600,000 miles?
I'm not. You're gonna have to show your trig for me to do it. All right. Here is for flat Earth. I don't know how this works, but that's quite amazing. That's how I think you're gonna have to explain it.
We're off to a bumpy start because I just showed you in the first video with just a little bit of lensing, like they say the atmosphere is a lens, backed the sun away, it disappeared, and it hit the bottom of the cloud.
So you think So how high is the cloud? How high did you measure the sun to be?
So I can demonstrate something, and in the same debate, you pretend you didn't even see it.
How
I literally
how high,
demonstrated it.
Brian? How high did you measure the sun to be over flat Earth?
Let me pull the trig for you, man, because I'm not going to let you weasel out of this one.
You want me just to show that again? Your video or no? I don't know if you want me to show that again.
Yeah, hold on a second, Jared. 1 second. I didn't think he'd have. I didn't think he'd argue the simple fact. But I'm just going to show. You know what?
Couldn't you just take the
ask the question.
circumference of the orbit of the sun and then divide by 360? If you want to get 1 degree.
Yeah, I'm just going to show this real quick. He wants to see the trig, so I'm just going to take a snapshot and send it real quick, if that's okay. And he can ask his question if you like. I skipped the question because I joined my condensed horizon earlier, so that's up to you. But I'll take a quick. This was important to me, so I thought we were going to keep this honest, and I don't feel like it's.
So you're showing the trig right now for your distance above the tangent. Brian, is that what we're looking for?
Is he?
I think that's what we're waiting.
He's focused. He's focused on something.
He's getting you the trig.
You know, when I spoke to Flatzoid, he was going to show me trig, but he never did. And then he'd point at something and he'd go, "There's the trig formula," but it was just plus and minus and multiply. There was no trig. I'm like, Flatzoid, there's no trig there. That's not a trig function. No, and here's the trig function. No, that's not a trig function. He goes, "Oh, but SOHCAHTOA." You know what that means? Well, yeah, it's SOHCAHTOA. But what's that mean? Well, it's for triangles, and that's a triangle. And I did the formula there. Thanks, Flatzoid. Good job. That's a good boy. That's no.
Brian, you looking for the trig or what? If he can hear me anymore, or what happened?
I don't know.
All right, we can move on to the next one until he's ready for that one. He can show you the trig after.
Yeah. All right, that's fair.
But Brian, you can hear us? Don't know what happened. Maybe he's off the tab or something, so it's not listening. We will give him 1 second.
I'll ship him some of my tab.
Oh, don't
so
do that. That's terrible.
He can be on the tab.
You know what's in that stuff? You know, if you drink one of those a day, Toon, just one a day, in 30 days, you have added a 5-pound bag of sugar.
In tab?
Yeah.
How did they get sugar in sugar-free tab?
Oh, is it sugar-free? I'm talking about. I'm actually talking about.
That's
Coke.
the point of tab.
Oh, I didn't know that.
Sugar-free.
I did not know that. My bad.
Yeah.
I was thinking it was a Coke, but now you just got fake sugar, which is even worse. So,
do you know what fake sugar is in tab?
Svedia or whatever stupid stuff is. I don't know.
No.
What is it?
It's saccharin. That's the one. That's the one in little pink packets at the restaurants.
I wouldn't touch those.
That's the one. I do prefer saccharin of the artificial sweeteners, though I generally don't like those. This though, the Toon Shine, that's the good stuff.
Oh,
there you go.
Brian can hear us.
Oh, do I look? I look more sophisticated. Watch this. Pinky up.
Wow, I'm impressed. I've got. Do you have any thermoses? I'm very impressed with thermoses keeping things cold.
I do have a thermos. It's another.
It's amazing. I can leave it out in the car and it's hot, and it will stay cold.
Yeah, it's insulative.
Brian, do you see us? Are you there? Are you coming back? Okay.
This is the longest snapshot of trig ever.
And I did really well of keeping everything 5 minutes, very, very packaged nicely.
So somebody here is asking, could you ask Jaren's thoughts on stevia leaves as a sweetener?
Yeah, I think it's probably the best that you can use, I guess.
Yeah.
But I don't like, you got to stay away from that processed stuff. It's killing everybody. That's why everybody is so damn fat.
Requiem for a Dream says, I only do artificial sweeteners because they help me poop.
All right. Thank you. Thanks for sharing. I'll tell my wife in case she has that problem. Brian, are you there? Does he see us? What is going on here? What happened?
I don't. Is he must be on a phone?
I'm not sure.
Oh my gosh, he's a strange one.
Okay, I'll
I
step
like
in.
Brian. I like Brian. He's so goofy.
I like Brian. You on the other hand?
What? Oh my gosh, it's a tough crowd, man. It's a tough crowd.
Okay, go ahead and name your next topic, and we'll see if that brings him back. I don't know.
It's his. Well, I mean,
what
it's
is he
his
trying to
turn.
find? The trig of saying that it was 1,000,000+ miles. Is that what it is? Couldn't you take because what it is now? I don't remember what his number was. It was like 1 point something million.
Yeah, he was applying the angle and then he's solving a triangle, I think, to get the
he's back.
the height of the other side of the
couldn't
triangle.
You just take
But
the
it's
orbit of
angle.
the sun and then that's 580 something, right? And then take that, divide by 360 and get 1 point something million? I think that's all that he was saying, but I'm not sure.
I posted the
Where'd you post
trig,
it?
but, in Telegram. It's just
You sent it to
the
me?
calculator.
Oh.
Telegram.
Yep.
It's just
I'll send it. Okay, I'll send it to Tim.
Put in for theta. I put in for theta 1 degree because the horizon is considered 0. We could do half a degree or a quarter of a degree. Doesn't matter how you want to do it. You put in 1 degree with a 93 million mile tangent in outer space, and you get an opposite side height of 1,600,000 miles.
Okay, I get what you're doing. I can explain it with my diagram here.
Okay, I'm moving this.
Right, here's the diagram. So when the observer is there, they're sitting somewhere here. I'll show you. Right, they're under the sun somewhere. You see that? Make sure I can.
You disagree with the trigonometry, Toon?
Just a second. They're sitting under the sun there. See that? And so the tangent to that person. This is not to scale, of course. So don't be confusing.
Oh, he's going to show it. Let's wait.
Yeah.
Okay. So there's the tangent for the person right there. And so we're looking at a theta there is negative, not positive.
Okay, so if I go up above the clouds,
the sun is below the clouds in this instant when you're talking about the tangent there.
Very good. So if I go up above the clouds, then the sun's going to follow me up, right? So if I go up 1,000 miles, the sun's still going to be at a tangent of my feet, right? It's still going to be 1 degree above the tangent of my feet, right? Way above the clouds, right?
It was never.
Warm out of this one, Dad.
It was never above your tangent. It was always below your tangent.
Right. It was no. It's 1 degree above my tangent.
Yeah, but in this example where you're looking at clouds lit from above or from below, you're over here looking up and seeing the clouds.
You disagree with a triangle calculator saying 1 degree above the tangent of my feet. When I just exampled, if I go above the clouds, the sun's going to follow me up. In fact, it'll follow me up all the way to the moon.
Brian, I'll say it only one more time. I disagree that the angle is above your tangent. I say the angle is below your tangent.
But just real quick, isn't the start?
Real quick, what if I'm on the moon and I have the same exact angle, damn near, as I had on the ground? A 1 degree shadow casted. I put a 1 meter stick in the ground. I've got about a 28 meter long shadow casted down 1 degree. If I go up 20 miles above the clouds, I've still got a downward 1 degree shadow, right? If I go up 1,000 miles, I've still got a downward 1 degree shadow. And you're disagreeing with the freaking triangle calculator?
Okay. I mean, I know I said I was only going to say it one more time, but I'll say it yet again.
We're talking past each other. Let's go to the next one. Toon, go ahead.
Good. Got it.
Unbelievable.
Right. So I, in addition to my $10,000 gravity challenge, I have the 1.5 year old challenge, and I've had really just one. I've had two, and Weiskopf is in my live chat here. But Brian, you are the only one really that I think, because Weiskopf didn't quite. I don't think you quite got what he was doing. You're the only one that has some sort of an attempt at this, and I appreciate your response. I appreciate your response. I said I don't think it's I don't think it qualifies because you use the globe. But I just want to say, just put it out there that the point of the gravity or the sextant challenge is to show how to do celestial navigation using only flat Earth. And again, like in the gravity challenge, any numbers you use, you need to show the derivation. So if you use 60 nautical miles per degree latitude or per degree from the GP of the star, you need to show the derivation of that, right? I can show the derivation of that for a globe because of the constantly changing angles. I do the math. When I do the math for flat Earth, I see that it must be an arctangent, but that's not the relationship that we see in reality. So I don't know where it would come from, and that's simply what I'm asking for. But again, the point is, I have the 3 angle measurements to the stars, and the challenge is to provide the process of doing celestial navigation using only flat Earth. And then you do that if you're within 25 miles, which is very generous. Then I'll send you a second set of stars, and you run the same process. And part of the reason, and I think like the Oakley guys, they don't quite understand why. The reason why I say you only need to be within 25 miles is because you don't need to then include refraction or dip angle. I made it super easy. And you know, when Flatzoid's like, well, dip angle, and Brian's logic is dip angle. Like, you don't even need to worry about that because with a 25-mile slop, you don't have to worry about that. Anyway, here's how it's done on the globe. This is the 3 stars. There's the one there, this little like cone thing that you see on the screen there. That's the GP of one star. Over on the right side is another. Down at the bottom is another. And then there's a circle of equal elevation drawn around those 3 points. The GP, this one here, see how big, that's a giant circle there. And then this one here, that's kind of just underneath Iceland. The circle goes around there. Is it orange, I think? Anyway, where those 3 circles meet, that is the point of the observer right there. And if we get close enough, we'll find the as usual, they don't exactly overlap because there's nothing perfect in meat space. So there you go. That's how it's done. So I'm not doing something that I can't do. So yeah, anyway, Brian, what do you think?
I could see this. I had a lot of fun on that show. It was a good show. I will say that, yeah, the refraction correction dip angle is a very minimal correction. I'll agree with you on that. For Reed, I'll say that I don't agree with the Reed. I'm not claiming. I'm not going around saying he owes me money. No, I mean, I was proud that I was able to figure that shit out. Never, always having used GPS myself, but for different reasons. Like you said that we couldn't use refraction. The way I come up with 3959 is I used trigonometry and put myself directly under Polaris, and then I moved 69 miles. And with a 1 degree change, and I got a height to Polaris of 3959. So I really wasn't using the radius of the Earth, but like I said, I'm not saying that you owe me because there were strict rules. But I would ask, why can't we use the Gleason's map? I think we should be able to use that. The way Globers complain about the Gleason's map, it does say as is, and Gleason was a flat earther, and I think there's a couple ways to do it on the Gleason's map, but I think when you take that away, you pretty much, I don't see how we could really do it, man. We got to draw our own map and then explain it. It makes it tough. I'll say that it makes it tough.
Brian, when I do, where do I have my I have the book here somewhere. I thought, there it is. All right. When I do in this book, this process for celestial navigation, right here, here's the book. This isn't using a map. This normal celestial navigation, how it's done commonly, there's no map involved actually. This just outputs the latitude, longitude. So, the Gleason map in the patent says it's an extortion from the globe. That's why you couldn't use it, because it's labeled as an extortion from the globe, right? If you use the Gleason map to do celestial navigation, you're admitting the Earth is a globe. But you don't have to use a map. This would work just fine. And when I did my $100
So I can do it in free
version,
space? I can do it.
What?
I can submit my answer and use free space.
and use free space.
Yeah, no map. Just I can do it in free space. In other words, matching the celestial sphere. I don't need a map.
Yeah, but I mean, you have to, the rules say if you're going to use the actual celestial sphere, which I find a little weird, but you have to provide a mapping mechanism between the celestial sphere and the coordinate system that you're going to be outputting in, right? And when I say mapping, I'm not meaning land mass mapping. I mean just some how are you putting the celestial sphere, which is not flat and doesn't map easily to a flatness? How are you mapping that to a flat? No, the celestial sphere is a full sphere, because there are southern hemisphere maps or stars, right?
What do you mean?
Half of the stars in the sky are in the southern hemisphere of the celestial sphere.
So who proved that? Ain't that what this debate's about? So you're just automatically assuming a hemisphere?
You're the one that said celestial sphere.
Right. Yeah, celestial dome. I should have said. Okay, correct me. But let me say one more thing.
Okay, dome. Okay.
Wait, before we move on, let me say one more thing. You act like you're measuring 69 miles per degree, and you speak of this a lot about these curve measurements. Can you directly measure curve, or do you have to, like you described earlier, you have to go off a straight line to derive your curve? So all curvature or calculations are second order measurements. You're not, every time you claim you're measuring curvature, second order calculations and whatnot. And basically you're would you agree with that? That you're not measuring curvature? I
have no problem with second order measurements. Very rarely does anybody ever do a first order measurement. It's extremely rare. So and it's not even second. It's probably third, fourth, fifth, sixth, or seventh order measurements is what you're actually doing if you're going to be real specific about it. But that doesn't matter. It doesn't change anything, right? You can't make a tape measure without doing some math to know where to put the second, third, fourth, fifth line. And when you're going to put a half inch, you have to do some math to know where to put that half inch mark. So,
okay, Brian, you're
up. Yeah. Anyway, go ahead.
Okay. So number 4. Okay.
Pressure gradients.
So pressure gradient. Once again, I wanted a demonstration because I gave you a demonstration of sun setting and not shrinking in size. I give you a demonstration of another light disappearing right in front of your face. I give you the refraction demonstration. And I also, I don't know if you've seen it on my channel, but I was able to demonstrate a pressure gradient inside of about 70 foot of PVC pipe by just heating up one side. About the last 10 foot I put in the gutter, and then the other last 10 foot I put in ice water. And I just left each end open-ended, and I loosened up a balloon and capped off each end. Well, what happened is that I was able to demonstrate on the hot side, it puffed the balloon up, demonstrating a gradient, and then I squeezed it to bounce the other side up to show that it's all continuous. And as soon as I let go, you see the other side dance, and then it went limp, and then the hot side, the pressure built right back up. So I was able to show a gradient. I was able to demonstrate a gradient in containment. So we ask you for pressure without containment, or a vacuum or near vacuum without containment, and y'all claim gradient. Well, I've demonstrated a gradient, so now I'm going to ask for a gradient without containment. We want to see some kind of demonstration without containment. We're able to show you all of the others.
All right. I got it right here. Here's my phone running the barometer app. Pressure 14.3091 PSI.
Welcome to Flat Earth.
14.3088
You agree?
psi. So I've shown you a pressure without containment, without a
What do you
physical container. Right here. From here
You just proved
to
we're
here.
contained.
The pressure changed from here to here, and there's no physical
So we're
container
contained
between.
then, right?
There's no physical container between here and here. I mean, you can see from here to here, there's no container. So I showed you pressure
No.
without a physical
There's
container.
There's no container halfway. There's no separation halfway in between my pipe either.
Yeah.
But there's the gradient. Okay, my point is we're arguing whether we're walking around in a contained area or not. Okay, you're just going to use that area to declare no containment. I can, like I said, I can demonstrate a vacuum in containment. I can demonstrate pressure in containment, and I can demonstrate the gradient you're speaking of that we have outside in containment. I can do it in 70 feet. Can you demonstrate any of them without just declaring?
Yeah, I could do it again.
No
I'll do it again. Right here. Here we
I'm
go.
going to welcome you to Flat Earth again.
No container between here and here. No container. No physical container.
Welcome to Flat Earth again.
That didn't show flat Earth. There's no explanation for this for flat Earth. What causes this pressure gradient?
Temperature. I just showed one way to do it.
But it's the same temperature.
You haven't showed me no way.
But it's the same temperature. Brian, it's the same temperature here. It's the same temperature.
Is it really?
Yeah.
Yeah, so you just proved that we're contained.
I proved that there's no necessary physical container for this, Brian.
I just explained how I can show a gradient inside containment. And you're backing it up saying, yeah, you're right. Look at my phone. I was going up and down.
So let me see if I can draw out a logical statement from that.
I'm asking for a demonstration.
Hold on. Let me just try this here. If there is containment and there is a gradient, if P then Q. Gradient, therefore containment. Q, therefore P.
Did you just double Q?
So you said if P, therefore Q. Q, therefore P. That's your argument?
No, did you just double Q? You said if containment and if gradient. Did you just double Q?
If containment, then gradient. Gradient, therefore containment. That's what you're saying, right?
Well, pressure. I'm trying to advance the argument.
Hold on. I want to make sure that I'm correctly stating your logical claim.
Containment, therefore pressure. Containment, therefore vacuum. Containment, therefore delta X or gradient of said.
Okay. Yeah. So you are saying if P then Q, Q therefore P. That's what you're saying.
Yeah. You can put it like that. I'm good with that. So
right.
what we're trying to do is
do you know what that's called?
Whether we're walking around.
Brian, what's that? What's that called?
Modus tollens or something?
No. Try again.
Syllogism?
Try again.
Just go ahead. Tell me. School me.
If P then Q, Q therefore P.
Modus ponens.
Modus ponens. That's right. That's what you just did.
My point is I'm trying to figure out whether we're contained or not. That's the argument, is whether the air around us is contained. And I'm trying to advance the argument a little bit. So I'm asking for a demonstration. I was able to demonstrate all the in containment.
Brian,
that's it.
Modus ponens is called affirming the consequent. You just did an affirming the consequent logical fallacy. And you are fine with that.
All right, I'll give you a point for that. I'll give you a point for the first one, which kind of was. So it's 7-2. Can't win them all, Tim.
Oh my gosh,
it's a good scoring system there. All right, who's up next? Brian, I think you're up.
Okay, man. I want to in my gap, man. Can I play my? This is to keep tune honest, man.
Okay.
See if you can.
One of the videos you already sent me or no?
Let me see. Did I send I don't believe I did. Real quick.
No, you only sent me 3.
If you want to ask, Yeah, it's actually Toon's turn. That was mine with the pressure gradient.
Oh, my bad. Toon, go ahead.
All right. Well, I'm going to share my screen.
Okay.
All right. This is an uncut video of the sun in Antarctica for 5 days. So there you go. It's a 2-minute video. I'll speed it up a little bit here. This is available on Vimeo. It's called "What Does the Sun Do at the Pole?" So 5 days time lapse of the sun going around counterclockwise here. So I don't know if you want to watch the whole thing or if you want to just respond.
Brian, you back?
Okay, I'm checking that one out. I'm checking that one out, and
Okay.
you say that's 5 days.
It's a 5-day time lapse of the sun going counterclockwise in Antarctica.
And it's exactly maintaining damn near the same height. So that must be right by North Pole. Can you give me the dates on that so I can match it up with the government with the .gov cameras? And I'd like to get a copy of that.
I can just send you to the page it's on Vimeo. It's called "What Does the Sun Do at the Pole?" And it's actually at the pole, and you can see these buildings here. These are different experiments that they have there. This is a telescope that's pointing straight up there. So
yeah, I'd like to. In fact, I'll even do this. I'll give you your third point in 7.3, and because I'd like to scrutinize that, and if it makes it through my test, then but I'd like to look into it and compare it to the .gov cameras and check the weather for that day.
Yeah.
We can almost always find holes in these videos,
Right.
but I'm not going to make assumptions.
Yeah, to be clear, this is not the North Pole.
South Pole, right?
Yeah.
That's it in Munson, Scott?
Yeah, at the actual, like, real close to the actual South Pole. And so, like, this particular telescope here, you can place. I've placed it before where it is, and its name. And then this other one that's coming up here, that one there, you can also look up. So
I just don't see the South Pole station. That's all. So it might be a little.
Yeah, I think it's off. Ellen. This might be it here. See that?
Okay, we'll look at
that building there.
Who lays claim to this video?
The guy, I forget his name.
I think it's
on
the
Vimeo.
Same guy who does all the videos.
Yeah, what's his name? His name is
starts on F. I don't remember.
Robert Schwartz.
Oh, there you go.
Yeah, Robert Schwartz. Oh my God.
I see that
All
your
right,
Schwartz
I'll
is as big
it.
as mine.
All right. What do we have left here?
Yeah, if you could play that one I just sent, man. That's the
okay.
The 5 with the
I got it. Bring it up.
the angle.
So this is starting your next subject here that we're going on to?
Yeah.
Okay.
This is with the angle. It's like 1 minute long, I think.
Okay. Give me a second. I'll bring it up. And we need to do.
Hold on. My for some reason my side froze for a second.
Okay.
I think I'm buffering or something.
That the radius.
White people problems.
Yeah, I am buffering. Yeah, my OBS hung. It's like,
oh, it happens to me sometimes. I can't stand it.
Sitting there spinning. Don't know
Sometimes it drops the.
Oh, there it goes. Okay, all right.
Okay, now you can see. We're ready to watch this.
No, just a second. Oh, dang. Oh yeah, that's it. Okay. Yeah. All right.
There it goes.
Is that the model predicts is itself an assumption.
No, you didn't pay attention to what I said. None of my presentation had any assumptions about the shape of the Earth. I assumed nothing. Nothing at all. On a flat surface, every triangle measures 180 degrees. On a sphere, every triangle measures more than 180 degrees. It's an absolute necessity. So if these added up to 180 exactly, Earth's flat. If they measure more than 180, Earth is not flat. All of these, more than 180 degrees.
But if we look down the page, we see, for example, triangle 2, triangle 3, and triangle 5 add up to a little bit less than 180 degrees.
And never do flat earthers ever take into account the details, right? They just say, well, it must have been from a certain level, but it's not. It's always wrong. Get your details right before you start talking about stuff. It seems like you were convinced by lack of detail and lack of critical thinking on how to actually analyze stuff. These triangles, these spherical triangles were measured. They were more than 180 degrees, every single one of them. That absolutely defeats the possibility that the surface of the Earth could be flat. No question about it, because they're not 180 degrees. Every one of them is more than 180 degrees.
But if we look down the page, we see, for example, triangle 2, triangle 3, and triangle 5 add up to a little bit less than 180 degrees.
Please address the actual evidence. They're on mountaintops or hilltops or on a tall structure that they built. There's nothing in the way.
I don't know what to say, man. I don't say. It seems like such a theological.
Maybe you should actually do some research on your own. Yeah. These things have been done for centuries, right? You didn't know about it because your Papa Flurf didn't tell you about it.
Okay, that's the topic.
All right.
Go ahead.
And so my question is do you feel like you owe Ryan an apology? Because you boldly claimed about 5 times, I just clipped out a few of them, that all the triangles measured aren't 180. So on a flat Earth, with the way we describe it, we would expect, some of the angles to be a little bit less and some of them to be real close to 180. And then probably around mountains and other regions, maybe more than 180, but always, skirting right around 180. That's what we would predict on a flat Earth. So do you concede now? Anything at all ever? No, I'm just saying, do you concede that you were wrong? That all the triangles aren't more than 180?
No, you didn't look at the correct number. We went over this before, but let's see here. I have the
first
publication.
Order.
Here it is. Okay, here it is. I have an example up of one of the ones that you might have been talking about. I'll share my screen here.
There's several first order measurements.
All right, here we go.
That are under 180.
Here we go. Here we have triangle number 2, only middle base, only west base, Buffalo Mountain. See that? Right? So this is the uncorrected values here. They sum up to just a little bit less than 180. That's the uncorrected values. But it's an intermediate step. When they're done, that triangle, the corrected values, that triangle comes up to 0.04 arc seconds over. Why? Because they're being precise. They're working hard to be as accurate as possible.
So they're retrofitting a model.
No, they're not.
What's the cause? What's the
okay?
Cause
all right.
For the correction?
Where are they retrofitting the model? Show where the model is being retrofitted in this book.
Maybe I'm
what
wrong.
Page? What page? No, no. You made that very specific claim.
And maybe I'm wrong.
Then why are you making the claim?
Well, I want to know, what are they correcting for?
All right, no, Brian, are you retracting your claim?
No, I'm asking, what are they correcting for?
All right, we're gonna go right to your claim. You are claiming that they are retrofitting the model.
You make a positive claim.
I said, are they retrofitting the model?
You said that they are retrofitting. What page are they retrofitting on?
Okay, well, I changed it to, are they?
Okay, are they? The answer is no, they are not retrofitting.
Okay, so what are they correcting for, please?
All right, can you see these pages here? So on these pages here, they're going through the correction. That's what all these pages are for, and I'll go up to. Well, you asked me to explain it. You're going to have to let me explain it.
I'm not asking for an explanation. I'm asking for what is the correction for.
Are you asking for an explanation, or are you not asking for an explanation? You're going to have to decide.
Measurement. You agree the first order measurements are less than 180?
No. What do you mean first order? When you say first order, what do you mean first order measurements. What do you mean by
Direct measurement. Direct.
that? Okay. Now what you're doing, Brian, is you're trying to apply my words to something other than what I was meaning when I was saying those words. So let me be very, very specific, Brian. When I said in that video that you showed of me, when I said all of it,
please. Don't be specific. Be honest.
just let me talk. All right.
Okay.
When I was saying that, I was specifically referring to these on the second column here, when they have done the corrections. You see that? That's what I'm talking about right here, because this is the most accurate triangle. That's what they're doing. And these pages and pages of things that they're doing here are to adjust for errors in their measurements and to get them out. And you see, they're always talking probable error of a single observation. They're talking about the residuals here. The residual is how much it's varying from the standard deviation, from the average, from the mean, from these different things. And they're making these equations here. They have a series of interrelated equations. They call them mingled. I forget the word they use in T.W. Wright's book. And then they're solving for these series of equations here, a very manual way, right? It'd be very quick to do it in Python today, but back in the day, the computers that they had were humans. Humans were computers, and the humans had to do all this work here, and they're doing all these adjustments. And so you see here this correction to 1.16. You see that? You go down and you find in one of the triangles where that they did that, you're going to find that 1.16 that they added in somewhere in one of these triangles, right? They're not, none of these equations here are retrofitting a model. What they're doing is they're correcting for errors, because these different triangles don't, when you measure them, they don't overlap at exactly the same point from different angles. So they know that there's something imprecise about it, and so they're doing everything they can to correct for those imprecisions.
MCToon, you're up.
So they know. They're begging the question, basically.
No, they're
maybe,
basically not begging the question.
They're
100%. They're 100% trying to be as precise and accurate as possible, and they're using this correction mechanisms that have been around for before this particular survey was done, written about by T.W. Wright in his book. That's open source. You can go grab and look at it and read it for yourself and see how these things that they're doing here is what T.W. Wright was talking about.
Okay,
What's
go ahead,
causing
Toon.
all these errors?
We'll follow that up.
All right, we can move on. We can move on.
What's the guy's name, real quick, Toon, on that book?
T.W. Wright.
Right, like WRIGHT.
WRI, yeah.
Thank you.
And
okay, go ahead.
I could be. It might not be TW. Oh, there it is. Yep. The process is so well understood as to need no further remarks. Reference may be made to T.W. Wright's Treatise on the Adjustment of the Observations, New York, 1884. There you go.
Thank you. You're up.
All right.
Your turn, Toon.
In the book, where is it? I have it. In the book Einstein wrote, I have it here somewhere. Anyway, it doesn't matter. In 1916, he wrote a book. And I'm going to share my screen here.
Oh, you are. Sorry.
So,
take
yeah.
it away from you.
He wrote a book, and in the book, he referenced two non-terrestrial measurements that measure Earth's orbit around the sun. And let me see. I'll pull up the page. So the one of them.
You're not sharing right now, I don't think.
You're correct. I will in a second. People are seeing what I'm doing here on my side. So one of them that he's talking about was aberration, and aberration. Don't get confused by aberration being what Airy was also looking at. It's similar, but it's not the exact same thing. So it was by James Bradley. So all right, I'll share this so you can see it. All right. James Bradley wrote this 1727. He published this. It's is where he measured aberration. He was looking for parallax, but he found aberration. It was a complete surprise. So little bit right there. Not a lot of diagrams, and the typesetting was a challenge, but it's a pretty cool thing to read. He did find then that there's these two columns here. We have the difference of declination by observation, and the difference of declination by hypothesis. And 4.5 seconds, 11.5 seconds to 12 seconds. So he was half a second off there, very, very close. 17.5 to 18.5 seconds, arc seconds. These are. He did this by measuring the star Eltanin, which is the brightest star in the Draco constellation. And Eltanin is 75 degrees in the ecliptic plane. So if you're looking at the celestial sphere, it is rather high in the celestial sphere. Where he measured it in England, that is visible year round. So anyway, here is an example of what aberration sort of is. You see where the are you seeing that diagram I'm sending there?
Mm-hmm.
Okay.
Yeah.
See, yeah, the person with the umbrella standing there with the rain coming straight down. And in order to not get wet while moving, you have to tip the umbrella forward. Somebody that's not running with you still sees the rain coming down. But if somebody is moving along with you, you see the rain coming at an angle. All right. Next one.
I would
here.
say I would. Oh, sorry.
I'm not done. Hold on. I'm not done. So what that does is that makes it so that stars, depending on where they are in the celestial sphere, will have a different behavior. But where they are versus where they appear to be is slightly different because of that diagram that I showed you a second ago. Here is what you see when looking straight up. So this is showing straight up to the celestial sphere to basically a 90 declination in the celestial sphere. They trace a circle throughout the year. And it's an ellipse everywhere else, and then at the ecliptic equator, they just draw a line. So here is the actual entry in Encyclopedia Britannica for 1910. So there you see the little ellipse there at the top there, and then it shows examples of a circle and then squishing down and then eventually a line. So the top one would be at 90 in the ecliptic sphere, and the bottom one is at the equator of the ecliptic sphere. So that is how one of the ways that we know that the Earth is orbiting the sun, because the aberration draws us varying squishinesses of ellipses throughout the year. And again, you can find this on my website, MCToon.net. Just search for orbit, and then you can find the Earth's orbit around the sun page. So,
All right. Yeah, I looked into this, and the irony, man, is that everything I've looked into is he had predictions. Okay, he said he was looking for parallax. They had the heliocentric predictions and they got unexpected results, which is another way of saying they were wrong. And they said they led to the first evidence that the Earth position is moving around the sun. Okay, so by measuring the star's position was their first direct evidence, they claim, that the Earth is what's moving, which ironically enough, with the Aries that he just showed the raindrops, it was in 1871. They Aries made also a prediction, which he got unexpected or wrong results, because they said they were trying to figure out whether the Earth were moving or the stars were moving. That was what was being debated back then. Some people might deny it, but that was the debate. And he come up with a simple test that if the light, let's call the light raindrops, okay? And and we have a cloud above us. So if the raindrops are moving independent of the cloud and they're coming straight down, then no matter what we do to slow that raindrop down, it's going to hit the bottom of the telescope. So by filling the telescope up with water, Aries predicted he would have to tilt the telescope to an additional certain amount to account for the fact that it's the Earth moving. So in other words, if the telescope's moving or the Earth is moving with the telescope sitting on it, and the raindrop is coming down the tube of the telescope, it's not going to make it all the way down to the bottom. It's going to hit the side of the telescope. This is common sense. But what they did instead is they got unexpected results, which I don't see really. And so what they did is they abolished the ether, I guess. They said it was in respect to ether, which still doesn't explain them not having to tilt the angle. But then in Michelson-Morley, which was...
Why are you changing the topic?
I'm almost done. This is all tying together.
It's a whole different topic.
Ironically enough, the next unexpected results proof of us moving, okay, and all these wind up being proof for special relativity, is that they got unexpected results or wrong results, and they re-abolished the ether because pretty much every prediction the globe makes, when it comes to direct observations of the Earth in motion, apply to measuring the stars moving and their unexpected results, which go on to somehow prove something else in the future. When they just re-explain it, and I had more to say, but I'll cut it short.
Well, yeah, we're good on that topic. Do you have another one left, or did you just skip around?
Yeah, I had a fun one. At the end.
Globe model buoyancy?
Yeah, just the heliocentric model buoyancy in general. And I'm not trying to. So this to me was a fun one. Like,
well, hold on a second. Hold on, I'm lost real quick. Didn't you go first? Toon went second.
Yeah, something.
So because you have none left, right? Toon, you have none left. I think we covered.
Oh yeah, I did not do reciprocal zenith angle measurements. I skipped my number 4.
Okay, so we got Toon up to finish off because you've done all yours, right, Brian?
I had one left.
No, he has one more.
Oh, he has one. Okay.
Yeah, he has another one.
Okay, go ahead.
Yeah. So this is kind of a fun one. Like, I just wanted to get people thinking. Like when they, I'm not trying to pin you down, but this is food for thought. So when we mentioned Helios, I could give 2 quick explanations of, to me, what would be head scratchers at the very least. So when we talk about the heliocentric model and the math of the buoyancy, I've asked several Glovers, if gravity increases, does buoyancy increase? And Ruif and Zanuck, others, they've all looked at it and agreed yes, that since gravity is in the equation, yeah, if gravity increases, buoyancy increases. So got me thinking about it got me thinking about how they claim that it rains diamonds on Jupiter, and first I was always thinking, to adjust the densities, they have to come up with absurd claims. But then when I was just thinking about the buoyancy, I was thinking, well, if to precipitate down, we have to be as dense as diamonds, then I would ask this, if we try to go and put a probe onto Jupiter, wouldn't it just bounce off? In other words, if we couldn't get it at least as dense as diamond, it would float up in the clouds. Am I right to say that anything we tried to land on Jupiter would just bounce off because it wouldn't be dense enough to make it to the surface?
There is not a strong agreement on whether or not there is an actual solid surface to Jupiter. Some think it may just be liquid. But yes, you would need to have whatever your probe is doing, it needs to be more dense than where it's going to be, or it would have to somehow accelerate itself downward, which would be kind of difficult. So yeah, if Jupiter is just increasing, say, gaseous density, then whatever probe, if you didn't go in at an extremely high rate, would eventually find some neutral buoyancy level within the planet, and then that's where it would rest. It could
All right.
potentially be beyond a liquid boundary too. I don't,
Fair enough. And
So,
then
yeah.
to end off mine, I was thinking, I was also trying to apply that. I had a couple conversations where I was thinking about Lagrange points, and I was thinking about the Earth and the center of the Earth. And I was thinking if we took in free space and we split a sphere dead in half and just separated the two half spheres, two flat sides of, and then, two hemispheres basically. And we just had them like a foot apart. And I was right in between both of them in free space. And I stuck my arms out. I stuck both arms out to tickle the center of one half sphere, and to tickle the other. I'd basically be in a Lagrange point. If I'm correct, that the new centers of mass would be the center of each one of them halves, or as close as you can get to the center. I would basically be pretty much weightless in a weightless area if I'm directly in between the two. So I would ask if I enclosed them two around me, and I had like a 5-foot bubble around me, just by moving them together, would that crush me? Would I be getting crushed by weightless mass? By weightless? I mean, it's just a.
All right,
thought,
I
right?
think I can explain some things there.
Okay.
If you had a hollowed out portion of the Earth right in the middle of the Earth, that's called a Dyson sphere, and inside that Dyson sphere, you would be weightless. If you were to slice the Earth in half and move them some distance away from the other, now you have two separate Earths, and each of them would have a separate new center of mass, and each of them being quite large would, if you say you move them far enough away from each other that they weren't close, then each of them would right away begin starting to collapse into a sphere again, to the working against the tensile strength of the materials that it's made out of. Yeah.
So
I don't know
crushed or
why
not
you're
crushed?
sticking your arms out and tickling them. I don't know, but you probably should not. Naughty boy.
Well, crushed or not crushed though? I didn't quite get it.
I don't know that. Let's say you're not slicing them. Instead, you're just hollowing out a center, a point in the middle, like a chamber in the middle that's 100 feet in diameter. You would be weightless inside there.
So I wouldn't get crushed. Okay. So
All right, you're up, Toon.
Thank you for that.
Now we know that's where they're
Thank you for
faking the ISS stuff is from the center of the Earth.
Yep, that definitely makes sense.
Okay, go, Brian.
All right, this is my last one, right?
Oh, yeah, sorry, Toon.
All right.
All right, I'm sharing my screen. All right, okay.
Okay,
Reciprocal zenith angles. Here is a diagram of the two cases that we're talking about. On the left, we have so reciprocal zenith angles is where you take two theodolites, you point them at each other, or one theodolite and you point it at a target, and then you swap where the theodolite and the target are, and you measure it again. On the left side, this is on the Earth. Those two lines that are kind of diverging from each other on either side, those are the vertical. And so you're going to put a theodolite, and the theodolite, then you will level it so that it knows so it gets things vertical and horizontal correctly. And then you measure the angle down to the other one, and down unless they're significantly different elevations, it's going to be down. If they're at the same elevation, they're going to be down on the globe. On the right side, we have what it would be like if the Earth were flat. You'd have this blue line, and the angle isn't. Don't get confused by the up angled lines there. You'd have a 90 on each side there. And so what you do then is you sum the two angles. If the angles sum to neglecting refraction, if the angles sum to 190, that would indicate that the Earth is flat. And if the angles sum to more than 180, that would indicate that the Earth is a globe. And then you'd want to take into account some refraction effects. And typically you do that afterwards because it's or you can measure the vertical temperature gradient like in that one paper I showed. Anyway, so here, Baron Rutledge, who has he's a surveyor, he went to the salt flats in Utah and he measured it. Here's his field notes. I put all of his notes into a spreadsheet. You can look at that. Just go to my website, search for Baron. You'll find it, Baron Rutledge. Here's his video. I'm not going to play the whole video, but here's his. Get out of here. There you go. So you can see the process he did. There's his theodolite. He's showing how he did it. Anyway, there's this diagram. So he measured it. He found it to be more than 180 degrees in all those instances. Here we have how much more, 0.004, which is 15 arc seconds. His measurements are accurate to better than, let's see, better than 1 second, I believe. Yeah, his standard deviation is 0.4. His standard deviation of mean is 0.2 arc seconds. So it's very likely, extremely likely, that he is precise enough there to confidently say that 15.2 arc seconds is correct. And then I'll give you one more thing. He's not the only one. It's been done many times. For example, it was done in the transcontinental triangulation American arc of the parallel. We spoke about that just a little bit ago. Here is the chart of first. Here's all the reciprocal zenith angle measurements. They were all typed in. Every single one of them in the book were typed in. Pages and pages of pairs of things that good people helped out, volunteered to type them in. And then it all breaks down to this chart right here. And each of these dots is the horizontal scale. Here is the distance between the stations. The vertical angle is the more than 180 degrees when they summed it up. And you can see this nice straight line going up there. And the top right there is almost 2.5 degrees of reciprocal zenith angle overage over 180. And it's nearly 300 kilometers from mountaintop to mountaintop. It's 2.353 degrees. This is on my website, mctoon.net/se. You can get to this exact worksheet or notebook. It's all published. Everybody can see it. You can look at all of the data here. Nothing is hidden or covered up. It's a ton of work that these people help do, typing in all the data. So we have Baron Rutledge on his own doing this, and we have people doing it in a professional survey 120 years ago.
Yeah, I would start by saying that when you're talking about the arc of the parallel at the 39th, their distance measurements, which they were really just pulling one side, and their margin of error, if you look up for pulling chains, was 1 to 100. So for every 100 miles, they were allowed a margin of error of a mile.
No.
Yeah, and then they improved that.
Brian, hold on. No, they did not have a 1 mile margin of error. They had a couple millimeter margin of error.
I'm not talking about the angles, Toon. Chill out.
I know you're talking about the baseline measurements.
Yes, I'm talking about the margin of error for pulling chains. Okay,
it's not a mile.
When they moved the tapes, they improved it to 1 in 1,000. Okay.
No.
When they improved it, dude, can I talk? You just know. You don't even know any of this shit. You just know. God, you're so dishonest, dude. Anyway, the thing I would say is when you give the Great Salt Lake example, I led off this debate showing you how Jesse Kozlowski and Tim Osmond, I'll have to send you the evidence for that, but it's known to a lot, where Strong's Knob, where his crosshairs were underneath the Great Salt Lake. So whether on a flat Earth, something's going on there, or on a globe, you know, that's not supposed to happen. So we're not seeing in pure geometry, but I put together, so in other words, if we tried to apply
Brian, all you've done is avoid the topic.
Shut up.
You've not touched the topic once that I brought up.
one minute to finish it off. Go ahead, Brian, you got a minute.
If you tried to measure reciprocal zenith angles to reality, like Skunk Bay, or you're going to get different shit all day long. I got a 1-minute video that says reciprocal zenith angles, Jaron. It's actually about 45, 55 seconds, man. If you can end it off with that.
Okay, we'll end it with that, and then get ready to do your conclusion, your closing. Reciprocal zenith angles. Okay, we're going to show this, and this will end it. Let me get this over here. Okay, here you go. Oops, that's not right. This one. Is that the video? Okay, here it goes.
Yeah,
this measured divergence from Larry and Jesse does not include the effects of refraction. And we're always looking through the atmosphere, and we always have some refraction. And refraction always makes objects in the distance appear higher than they really are. Not by a lot, but by some amount. That's what the green dots are simulating. Larry, down there on the left at the red dot, was looking at Jesse, but he was seeing Jesse up there where the green dot is. He was seeing Jesse in a higher position than Jesse actually is. And that made Larry's angle A smaller than it really is in reality. The same thing. And that made Larry's angle A smaller than it really is in reality. The same thing was happening to Jesse. Jesse was looking down at Larry. He's now the green dot on the left side. And again, the effect of refraction is to decrease the angular measurement that Jesse's making.
So there you see, look at his crosshairs. That's Jesse's Larry's crosshairs looking back at Jesse. Look at the tripod. And I mean, just that little bit that it's cheated down, and the fact they're assuming refraction, you know, that's why I wanted demonstrations of all these refraction measurements to make their shit work. Because as Toon showed you, he didn't want to concede, but he showed that the first order measurements showed angles less than 180. I know this is a different measurement, but it still all goes hand in hand. He can't claim refraction side to side with a horizontal measurement, but he'll just give me a bunch of numbers and say, well, they correct, but he won't give me a cause, you know. And this is just another example where they're just retrofitting their model, man. You've seen that in reality he's looking lower, you know. It's just, you know, prove
if
that.
If you're gonna claim retrofit, you need to show specifically where it's happening, because you've made a claim, and as Austin says,
positive claims have the burden of proof.
You have the burden of proof. So if the model is being retrofit, show exactly where it's being retrofit.
Okay, what I showed you earlier was the way you describe refraction working is you say that light bends toward the denser medium. Okay, so I showed you on a warehouse floor that ain't the case. I showed you in sugar water that you say we're supposed to see things higher, but that ain't what we've seen in the sugar water. We literally seen the Toronto skyline lower than before he added the sugar water. So I can agree with you all day long that, hey, light's refracting downward toward the denser medium, but the resulting claims are just baseless assertions. You're demonstrating things appearing lower and claiming that they're higher. It's baseless assertions. That's all you've gave us nothing but baseless assertions all night. You haven't conceded one thing. You won't give me a cause for these corrections for the first order measurements.
I gave you a cause. You didn't pay attention.
You're dishonest with the first question, man.
Okay, Brian, let me give you got your 2 minutes to do your outro.
Yeah.
Go ahead.
I'll keep it down to about a minute of bitching about Toon.
Okay. But this is your time. This is your time to do it. So
I feel like we need to demand more demonstrations. All these baseless assertions, all these claims. I showed demonstrations. I've got videos of demonstrations with gradients inside containment. I've got demonstrations of dropping 2 size balls and one falling faster with the same air resistance. And I've got demonstrations of light disappearing right in front of your face. And next week, MCToon's going to say, how's the sunset? He's going to try and hold us to strict geometry when the atmosphere is obviously lensing in either model. And they want to hold us to strict geometry, but they want to use refraction and just use anything to correct some of their shit. Now I guess they're claiming side-to-side refraction in the cross-country arc of the parallel, the 39th parallel. Like, he never gave us a cause for that. He got pretty upset about it, but he still never gave us a cause. So what I ask is for demonstrations of of not what's happening. I want to see it happening in real life. The way flat earthers demonstrate and show you things, scale them, show us these orbits, show us refraction doing what you claim it does, show us these gradients, show us pressure without containment, show us anything at all, ever. Thank you.
Thanks, Brian. All right, Toon, you got 2 minutes.
All right. Well, multiple times I gave you the cause of the triangles being corrected, and you never heard it, so I'll say it again. The cause is that there is nothing perfect in meat space. The lines do not precisely meet at one exact point, and these differences are called residuals. And so these equations and the formulas and the correction process by T.W. Wright is correcting for these in that process. So the first order triangles are the final number. The first number that you're reading there is not the first order. That is the intermediate step. That is not the final step. The final includes the corrections. So every one of those, no exceptions, every one of those in the final values with the corrections are more than 180 degrees. You did not one time talk about the reciprocal zenith angles that I brought up. You went right to a different topic. I brought up aberration as measured by James Bradley. You immediately deflected to talk about Airy's experiment, a completely different thing. You didn't address the topic at all. You must have just seen aberration and thought, oh, that must be this other one. So I covered all of those things. I gave you exact demonstrations in the write-ups that were done. Doesn't have to be a video. Demonstrations aren't done in just videos, Brian. Big people can handle things that aren't just written in videos. They can actually have things that are written down, because that's part of the scientific process, right? You do all of your experiments and then you share it to the scientific community. That's not generally done in video form. That's generally done by writing it up, and then they have supplementary information. Sometimes videos, a lot of the time pictures and diagrams and data, raw data sometimes. So anyway, Jared, thanks. It's been fun. Brian, I like talking to you, man. That
seemed honest. Thanks, Toon. Thanks, Brian.
Yeah, thank you.
There is one.
Michael. Thank you, Joe.
I thought I saw one super chat come through. Let me just check what that was, if it was for one of you. Thank you, Slavery is a Choice, for becoming a member. And then we got The World is Rigged, says, you guys have been doing these debates for a long time. Do you really think they're helping? That's a good question. Toon, do you think any of the debates you've been doing are helping?
I think so. I sometimes get people that message me and say, hey, I used to toy with flat earther. I used to be a flat earther, but no more. And so I would say that's good. And I have to figure that most people, if they somehow see this and then were toying with the idea and then decided, oh, that doesn't make sense, they're probably not going to contact me. I think that so it's a little bit nebulous. How effective? I don't know. I'm having fun. I'm entertaining myself. I'm educating myself. I hope that I'm educating other people, and that we could then call this edutainment. So,
yeah, I've learned a lot through the debates, man. I've learned a lot from Toon, a lot from even Blue Marble Science. I showed some of his. I think these debates are the closest we're going to get to any kind of truth, because people can hear unadulterated, unedited version. No straw man, we're each stating our case. And, and hopefully this is how we narrow the argument down at the very least.
Yeah. And for me, the reason I like doing these debates, to do these debates is because otherwise, if you get into an echo chamber, you're certainly not learning anything. You're certainly not growing. So it is good to hear from people's beliefs. Give me your honest beliefs. Give me your claim. Let me hear it. And then it's up to the person watching to decide what better matches their reality or their worldview. So that's why I think it is beneficial to even me to listen to both guys give their sides, and then also it gives me a lot to talk about like this coming week. So for me, I'm liking it. There's lots of things I have down that Toon talked about that I need to look into and then report back. So for me, it's all good. We are going to work on the time thing. I'll figure out, I'm going to go back to the drawing board a little bit and think about ways to keep the time shorter. Some of these topics, they got on and they spent, 4 minutes on the just laying it out there, and then it's difficult to have a conversation in 44 seconds. So anyway, it'll get better. Thank you very much. Curtis Flatter, thank you very much for that super chat. And I believe that's it. Yeah, it's been fun, guys. We will be back Thursday, I believe, for Speaker's Corner. And any final words from you guys?
Yeah, thank you again, Jaron. Thank you again, Michael. Always a pleasure, man. I got a few things to look into. You gave me, I hope I gave you some food for thought. A couple of things to look into. Maybe we can, like I said, consolidate our arguments, police our own, and keep this going. And maybe at the very least, shrink the arguments down to the direct meat of it. Thanks again.
Toon, final words, or is
All
that
right.
it for you?
I kind of already did.
Okay,
Thanks a lot. It's been good, and I look forward to doing it again. So 5G. I keep looking for. Oh,
that's you want to do 5G?
Yes. Somebody come and challenge me to 5G, because 5G is safer.
Toon thinks 5G is healthy for you. So if you're somebody who disagrees,
safer.
Oh, safer for you. Then what?
Yeah.
Then 4G.
Then 4G or 3G.
Okay. All right.
Yeah.
So if somebody wants to debate that, you can do so right here on Debatism. All right, guys, it's been fun. I am trying to get my outro to play, but it's not working here.
All right. I'll say bye and
Peace out.
myself here.
Later, guys. All right. And I don't know why this is not working. There we go. Now it'll work. All right, guys, we will see you Thursday. If you need me or want to reach out.
With his decadent sludge.